So, good morning everyone. My name is Giuseppe and I come from the University of Messina. First of all, I would like to say thanks to the scientific organizers for this opportunity. Also, it is here to share with you part of my thesis project. As you can see, today we are going to talk about the potential application of citrus waste in the context of circular economy model to obtain polyvinyl alcohol-based bioplastics for food packaging application. Infatti, in the circular economy model that was officially adopted in Europe in 2015 with the Circular Economy Action Plan, what is considered waste in the linear economy model is reintroduced into the production chain to generate new economic value and reduce also environmental pollution. So in this context, we can obviously say that bioplastics are very important because they are plastics made from bio-based polymers or synthesized from petroleum-based polymers like polyvinyl alcohol that are biodegradable. So they are part of a circular economy system in which these polymers are produced from renewable or recycled raw materials. But the question is why today there is a growing interest about food packaging and about bioplastics. That if we search, for example, on PubMed, we will see a lot of results about the about articles in bioplastics and food packaging application. We can say that today the annual plastic production is about 318 million tons, and it's increasing with an annual rate of 4%. So as a result, today we have a million tons of plastic waste that have been generated since 1950. So there is a growing attention today about the environmental impact of plastic waste that is driving the transition to a circular plastics economy model where reuse and recycling dominate the life cycles of materials. Moreover, the application of the circular economy is also important because it reduces the production of waste that in most of the case ends up in the sea, generating, for example, several problems like the production of microplastics particles. So, in this context, we can observe say that the smartest solution to reduce the production of plastic waste and obviously to reduce also environmental pollution is the formulation of eco-friendly and biodegradable food packaging produced from bio-based resources, and this smartest solution received a lot of attention in the last 10 years because these bioplastics, in addition to their productive role, are also able to deliver biological compound from food waste, for example, also polyphenols, and in this way they can modify the mechanical characteristics and also add new properties like the antioxidant and the antimicrobial. So based on these attractive properties, our research focused on bioplastics produced from polyvinyl alcohol, that is a petroleum-based polymer, but is biodegradable, unlike the others petroleum-based. For this work, we decided to modify polyvinyl alcohol with polyphenols and carbohydrate fraction obtained from citrus bergamot waste, a product that is also called pastazzo. Pastazzo is essentially a byproduct usually obtained from the industrial processing of citrus fruits into dyes and essential oils, but pastazzo is really a potential rich source of biological active compound like polyphenols and carbohydrates. So we decided to obtain, using a green extraction technique, all the polyphenols that are still present inside the pastazzo and also the soluble carbohydrates, and then with another enzymatic digestion using pectinase and cellulase, we also recovered all the solid carbohydrates inside the pastazzo, and in this way we obtained the new citrus and polyvinyl alcohol-based bioplastics. Then we characterized, for example, a lot of properties about these bioplastics, like the optical properties, the colorimetric analysis, the morphofunctional characterization, and also we analyzed the antioxidant characteristics, and finally we demonstrated the potential application of these bioplastics for food packaging application. So, as you can see, in the linear economy model, citrus fruits are only used to obtain dyes and essential oils, but the pastazzo that we produced in this way is only disposed. So in our work, we decided to reintroduce the pastazzo inside the circular economy model we recovered all the polyphenols by green sonication technique, and then we analyzed and quantified all the polyphenols using HPLC DAD. After removing the polyphenols and analyzing the composition, we reintroduced the passato for an enzymatic extraction with pectinate and cellulose to release and facilitate the solubilization of pectins and polysaccharide, and in this way we obtained the different metrics that we used to analyze to obtain these citrus and polyvinyl alcohol-based bioplastics using the casting method. After the first step that we carried out, that we have already described, we also carried out the morpho functional characterization of the new bioplastics using X-ray SEM and FTIR to see if the structure of our materials changed after the functionalization with polyphenols, soluble carbohydrates, and also with the solid carbohydrates and polysaccharide obtained after the enzymatic digestion with pectinate and cellulose. Then we analyzed all the optical properties for these bioplastics, in particular, for example, the transmittance, the opacity, and also the colorimetric analysis to show the difference before and after the functionalization of polyvinyl alcohol. Then we also analyzed the antioxidant activity because the addition of polyphenols recovered from passato opened up the possibility for active packaging. So we have carried out some of the most widely used antioxidant in vitro to see if our bioplastics really meet the definition of active packaging with new antioxidant properties. And finally, we understand how the plastics produced from citrus waste really useful for food packaging. We also analyzed the shelf life of purple samples with and without plastics in a specific time period. Now, moving on the results, we can start to see the polyphenols obtained by green extraction because we have to say that in literature the reference method of extracting polyphenols from this matrix is a substrate with 50% of dimethylformamide in water. But obviously, dimethylformamide is not a green solvent, so we decided to use a greener method, and we saw that the best yield in a green way was obtained by sonication at 70 degrees for 15 minutes using a 70% of solution in water. The chromatogram, you can see, was acquired at 278 nanometers and rolled out to identify and quantify the following polyphenols. After that, we subjected our passato to an enzymatic degradation with pectinate and cellulose to facilitate the release and the solubilization of pectins and polysaccharides. In this way, we reused all the things through using the casting method to obtain these new bioplastics, where we have always 30% of recovered polyphenols and soluble carbohydrates, and in some cases we also have the solid fraction obtained after the enzymatic digestion with pectinate and cellulose. In this way, we obtained other two bioplastics with 0.5 and 1 grams of solid carbohydrates obtained after the enzymatic digestion. Now we can go to the morpho-functional characterization, and we can start with X-ray that show the crystalline structure of polyvinyl alcohol with a typical angle of 20 degrees. That is characteristics of this polymer. As you can see, for example, in this graph, we will see that after the addition of polyphenols and soluble carbohydrates, we will see we continue to see the typical crystalline structure of polyvinyl. So in this case, we haven't a lot of change, but after the addition of the solid carbohydrates obtained with the enzymatic digestion, we will see, for example, new peaks at 13 and 24 degrees. Then we can go to the same image that show different surface morphology, ranging from relatively smooth surface to highly rough surface. In the first case, after the addition of polyphenols and soluble carbohydrates, we doesn't influence a lot the surface morphology. We have only an increase in roughness. But after the addition of the solid fraction, as you can see, we have a more complex structure. So in this case, we haven't, as we saw also for X-ray, a very crystalline structure. And finally, for the morphofunctional characterization, we can go to FTIR, because first spectrum, we can see the typical PVA absorption band. Then, the modification of the starting materials with polyphenols doesn't induce the creation, for example, of new bands. So we haven't the formation of covalent bonds or other new bonds, indicating only a dispersion of the materials inside the polyvinyl alcohol. Then the other modification, for example, change the structure of polyvinyl alcohol, because we can see, for example, the typical fingerprints of cellulose in this region. Then all the bioplastics were also analyzed in terms of transmittance and opacity, that are parameters considered very essential for plastics used in the food packaging industry, because they indicate the amount of UV visible light that can pass through the materials and induce, for example, change in food matrix. As you can see, alcohol is a very transparent material, because allows to all the light to pass through the material, but after the functionalization we will see very important decrease. So in this case, less light can pass through the materials, and it means that we can decrease the possibility to have oxidative process like lipid peroxidation in food matrix. Then we performed also the colorimetric analysis that show the change in the color of bioplastics before and after the functionalization of polyvinyl alcohol, and we also performed this analysis with the colorimeter, that in this case we can see all the parameters that change after the functionalization with polyphenols and solid carbohydrates. And to understand if the polyphenols that we added, for example, can add the new properties like the antioxidant, we performed the most used antioxidant in vitro assay like the PPH, BTS, PRAP, and QTRAC. So, as you can see from the graph, only polyvinyl alcohol doesn't show any antioxidant activity before the functionalization, so without the polyphenols matrix. So these results reported and confirm that the functionalization of polyvinyl alcohol with citrus waste gives new antioxidant activity, so we can protect the food matrix and increase also the shelf life and preserve, for example, the organoleptic properties of our food matrix. In this case, the polyphenols that we recovered are very important because they make these biofilms fully part of the concept of active packaging, where the incorporated compounds act according to their direct release to the food or the environment. Finally, to see if our bioplastics could improve the shelf life of foods, we performed the food fresh cheming test. So we analyzed some parameters for 2 days on Malus domestica. In fact, we obtained this rectangular bag from the plastics. We put apple sample inside, and in this way we produced a different sample with only polyvinyl alcohol, with polyvinyl alcohol after the functionalization, and obviously apple sample without packaging. And then we analyzed the scavenger activity of apple sample with antioxidant assay and also with the colorimetric analysis. For example, after 1 day from the beginning of the process, we can see a significant decrease in the antioxidant activity of apple sample, but for all apple sample packed inside the functionalized bioplastics, we see a different behavior because the scavenger activity is comparable to the control. After 2 days, also for the bioplastics, for the apple sample inside the functionalized bioplastics, we see a reduction of the antioxidant potential about 50 and 40% compared to the control, but it's always better than apple sample alone or apple sample with only polyvinyl alcohol. And also this colorimetric analysis show and confirm what we said, and that in this case with our bioplastics we can improve the shelf life of sample and so reduce, for example, lipid oxidation and other oxidative process in our food matrix. So in conclusion, we can say that in this way demonstrated that citrus waste can be very useful to improve the properties of polyvinyl alcohol and give new, for example, properties like the antioxidant and increase the shelf life of food matrix. It's also important that our previous result already published confirm the importance of natural world for circular economy application and to obtain active food packaging. For example, in this case, we used chloroquine. We used also anthocyanins with polyvinyl alcohol, but also with ketone. In collaboration, we did some of this article in collaboration with the lab of Prof. Giuseppe and Prof. Visco from the University of Naples and University of Messina. So in conclusion, I would like to say thanks. Thank you for the attention. And obviously special thanks to my group at the University of Messina, and a special thanks to my supervisor, Prof. Davide Barrega, for giving me the opportunity to work on this project, and again to all the other colleagues from the University of Naples and the University of Messina.